Okay, so welcome to this first video in the playlist on abstract algebra. Okay, so in this video what we're going to do is introduce the whole topic of abstract algebra, and we're going to start with the starting place for everything really, which is group theory. We're going to discuss what a group actually is. Okay, so the structure of this video then, we're going to start off with asking the question, what is algebra? Because that's the motivation for what a group is. I want you to understand why we care, okay? Then what we're going to talk about is the actual definitions of a group, a little bit on the notation of groups. We'll talk about a definition, what an abelian group is, and then we'll give an example. Okay, right, so let's start with the question of what is algebra. Now this is very close to what is maths. Okay, so what is algebra? What does it mean to be able to add two numbers together or multiply two numbers together? Okay, so let's look at the set of natural numbers. Okay, so the set of natural numbers is the set of all counting numbers. Okay, so this is the set where we have 1, 2, 3, 4, etc. All of these in here. Now this is not going to be a group, but I think it's a good place to start if we're going to understand what algebra is. We're going to see the motivation for this. Okay, now, I know that these symbols here, and you have to acknowledge that these are just symbols now. They're squiggles on a page. Okay, I know that these have a deep meaning to you. I know that they capture a very real meaning, i.e. this symbol captures the fact that you can have one cow. This symbol captures the fact that you can have two cows, double the number of cows. Okay, so this symbolic structure can be used to understand a real world problem like how many cows do I have, and keep track of things like that. So it's very powerful, but for now I just want you to view it as symbols. Symbols on a piece of paper. Okay, so forget the fact that this was made to understand a real world problem. Forget the fact that it captures a real world structure, okay? That's why it's so fantastically powerful, but we just want to study it for its true structure rather than thinking of it in terms of the real world, okay? And that's really what abstract algebra is all about. Rather than creating algebras to mirror structure that's within the real world, which is therefore useful to us. Instead, what abstract algebra is about is creating structures that potentially have no real world structure that they mirror. Okay, or at least we haven't found any real world structure that they mirror yet. And then studying them for their algebraic properties rather than studying them for the fact that they mirror a very useful real world structure. Okay, so we're going to define structures not because they're useful in mirroring real world problems, but because they have interesting algebraic properties in their own right, okay? And that really is what group theory is all about. It's about saying, okay, we don't care about creating number systems that are useful for counting sheep, for instance. Now we're going to create number systems simply because they have interesting algebraic properties. Now what do I mean by interesting algebraic properties? Well, it means that we're going to be able to solve equations in them. Okay, but I'm getting a little bit ahead of myself. So, we have got this set of symbols here, and you can add two of them together. You can ask, for instance, what is 2 plus 3? And it will give you another symbol in the set. So what does that actually mean? Well, the generalization of this is that we could draw out a great big composition table like so, and we could put every single element up here. So we could put 1, 2, 3, 4, 5, 6, and we could go on. We could continue putting every single natural number here. I'll go up to 10, okay, but then it will go on, obviously. And then along this side, we could put every single natural number again, okay, and then fundamentally what we have done is defined what each one added together. So this is the composition of added together. We have gone through and decided what each one would be, okay? So 1 plus 1 is going to be 2, 2 plus 1 is going to be 3, again 2 plus 1 on this side is going to be 3 again, 2 plus 2 is going to be 4, 1 plus 3 is going to be 4, 3 plus 1 is going to be 4, okay, 4 plus 1 is going to be 5, 2 plus 3 is going to be 5, 5, 5. So, if we wanted to generalize the concept of having two symbols added together like this, all we'd have to do is create a great big composition table like this, and then just define what we were going to have in each one of these sockets. So actually, all you need to do to create an algebraic structure is this. You start by creating a set of symbols, okay, and this is very important that you understand that we're not thinking real world here now. We are doing abstract algebra. These are now just symbols to us. Forget the fact that this structure is incredibly powerful because it mirrors a real world problem. Forget that for now. Just think of creating symbols. So we'll create some garble symbols then. Okay, so let's sort of create some garble symbols. Oh, there we are. We'll have that as our first symbol. Which other symbols can I create that are garble? Okay, maybe something like that. Okay, I'll do backwards symbols. What about that? There, backwards 5, because that looks like a backwards 4. Okay, so there we go. I've created 3 little symbols. Now, of course, my little set here is a nice finite little set. The natural numbers was an infinite set, so it wasn't finite, okay, so it went on forever, okay, but I can create an algebraic structure on my little set just the same. All I do is I put my 3 little symbols in a composition table just like this, one that we had here, okay, and so I'll put all of these up here, and then also down here. And then I can call this composition whatever I like, basically. And the general notation that people now adopt for abstract composition is they just put a circle like that. Okay, so here is my final symbol. So, then I can put in whichever elements I want here. So I can make it up, basically. So I could put in this backwards 4 here, I could put in the backwards 5 there, I could put in the backwards 5 there, I could put in this symbol here, I could put in this one here again, okay, and I'm just making this up completely out of my head, okay, and this one here. So, I have defined you a composition law on this set now. So all a composition law is you draw a composition table like this and define what each symbol composed with each other symbol is going to be. So now if I pick any 2 symbols, if I say what is this symbol composed with this symbol, you can go to this composition table and you can say, okay, this one composed with this one, it's equal to this one, okay, and you can come up with the answer. Okay, so that is the generalization of addition, basically, or of multiplication. They're the same thing. They're just compositions. Okay, so you create a set of symbols and you define a composition table. So that is the generalization of what it means to add, multiply symbols together. Okay, right. Now, is that what a group is then? You just create a set and then define a composition law like this, and that's what this is called. It's called a composition law, and of course on the natural numbers we had a nice composition law. We had addition was our composition law. Well, no, that is not the definition of a group. In order for it to make it a group, this composition law has to obey nice properties that mean that you can solve equations within this structure. Okay, now you can see, looking at this composition table here, the little bit that we drew out, you don't need to know anything about group theory to see that this has, or abstract algebra even, to see that this has some beautiful patterns. There are these diagonal lines here, whereas this one, I just made it up, okay? So we're going to insist that there are some beautiful patterns within this composition law, and then we will turn this thing into a group, basically. So, overall then, what we are trying to do is generalize what it means to add things together and multiply things together. So this is about maturing in maths. All along in your life, probably, you have been studying maths, and you've been studying the same old number systems. When you were, I don't know how old, you learnt the rational number system, okay? So you learnt fractions, and you knew how to add them together, multiply them together. Then you took it a little further, you went to the real numbers, where you again had two composition laws. You had addition and multiplication. Now these are not groups. Well, they are groups, but they actually are more complicated than groups because they have two composition laws on. In order to be a group, you only need one composition law on. But the point is, we're now trying to generalize. We're saying, why are those the only number systems you can create? Why can't we create other ones? Now, yes, this might be useless for counting sheep, okay? But it still might be interesting as far as algebraic properties are concerned. So rather than creating number systems to understand how to count sheep, or to make a mirror structure that mirrors the structure that's in the real world structure, i.e. counting sheep, instead we're going to make structures like this that aren't necessarily useful for any real world job, but have interesting algebraic properties. And the interesting algebraic property we want them to have is that we can solve the most simple form of equation in this number system. Okay, so what do I mean by the most simple form of equation? Well, basically, if I wrote an equation like this, x, which is anything composed with, let's say, symbol here, is equal to, and I'll have to try and find something that actually works for this. Oh, good, it will actually work whichever one I put in. And I didn't plan that. Okay, so x composed with a backwards 5 is equal to backwards 4. Okay, so I want to be able to solve that equation. I want to be able to find what numbers, what symbols in my set would satisfy that, i.e. if you put them in place of x, which symbols would make this true. So for instance, if I put in the symbol backwards 5 here, if I put backwards 5 in there, I'll get backwards 5 composed with backwards 5. That would give me this sand timer symbol. So that would not satisfy this equation. Okay? If I put in sand timer symbol in here, then I'd get sand timer symbol composed with 5, and that would give me 5. So that, backwards 5, that would not, again, would not satisfy this equation. Whereas if I put backwards 4 in here, backwards 4 composed with backwards 5 is equal to backwards 4. So backwards 4 is the only symbol in my set that would obey this equation, that would satisfy this equation. Okay, so the solution in this case is x is equal to backwards 4. Now, did we actually solve that? Well, we did. We did solve it, but we did it by brute force. The mechanism we used was brute force. We went through every single member of the set and just tried to find which one satisfied the equations and therefore which one didn't. And I want to stress that nothing about what I did meant that there could only be one solution. That was just, that was luck in this case, because I could have had this as backwards 4 here as well, in which case sand timer symbol would have satisfied the equation as well. So we want to put constraints on this composition law so that there is a way of solving the equations even without using brute force. Okay, so we want to constrain the composition law somewhat so that it's easier and has beautiful algebraic properties. Okay, so how are we going to do this? Well, basically, we're going to ensure that there are a bunch of axioms on this composition law. So, let's think ourselves through this. How could we come up with a mechanism of solving equations? Well, it's a good idea to go back to a structure where you can solve equations already. Now, you can't actually solve equations in this structure because it isn't actually a group. You know this structure very well, so you know how to solve equations in it, but you know how to solve equations in it because you know the bigger structure that it's within. Okay, so the bigger structure that the natural numbers are within is the integers, okay, which contains 0 and the negative numbers as well. So this will contain 0, 1, -1, all the whole numbers basically, 2, -2. Okay, so this will go on and on and on. So I shouldn't have ended that set there. It'll go on and on and on. Okay, right. So, how can we solve equations in the integers? Well, let me give you an example of this exact same sort of thing in the integers. So we'll have x, and here in the integers you don't put composition symbol anymore, you put plus, but that's just another symbol for this same thing. So this is a specific algebra for which you use this symbol to mean composition rather than this symbol. Okay, and next have x plus 5 is equal to 7. Okay, and you could have chosen whichever 2 you wanted there. So how would you solve this? Okay, well, what we would do, strictly speaking, is what we'd say is x plus 5, and then what we'd do is we'd take whatever that was equal to, because x plus 5 has an answer. Whatever x is, you can add 5 to it, and that will be some element of this set. And then you can add to it another symbol. You can add to it, you can compose it with the symbol -5. And as long as you do that to both sides, then the equation should still be true. Because if what's on this side truly was equal to this side, then when you compose this side with the symbol -5, and you compose this side with the symbol -5, you should end up with the same thing, basically. You should end up with the same new symbol in the set. And I want to stress something, that it is now important that you're saying it composed on this side. Okay, so just look at this composition law over here. It was not necessary at all that, to take an example, sand timer composed with backwards 4, which I read as this one then composed with backwards 4. It's not at all necessary that that is equal to backwards 4 composed with sand timer, which is this one then composed with sand timer, which now equals sand timer rather than backwards 5. So it's not necessary that it is commutative. Okay, so the name for a composition law that is symmetric in this way is to call it commutative. Okay, let me just put this here, commutative. Okay, so if this composition law was commutative, then it would basically be symmetric along this diagonal. So anything like here would have the same thing on its when you take the mirror image in this diagonal. So if you rotate, well, if you take the mirror image, it should be the same. That would be commutative if this one here wasn't non-symmetric in the diagonal, because these two are the same and these two are the same here. So it's almost commutative, but it's not because of these two. Okay, so back to our question here. Okay, now what you can do is you can apply a law known as the associative law. You can say that x plus this symbol 5, and then that plus -5 is actually the same as x plus 5 plus -5. And that's not trivial, okay? Understand that that is not trivial. It's not trivial to say that x plus a, and then the product of that plus b is the same as x plus the product of a plus b. And let me show you that on this old composition law that we've come up with here. This is actually the most difficult axiom of groups to understand. This property is very, very difficult to pin down. Okay, so let's do an example with our arbitrary composition law that I came up with here to show that this isn't necessarily always true. If you just come up with a random composition law like this, it won't be true. So for instance, if we take x plus backwards 4 like this, and then we'll compose it with backwards 5, let's put sand timer in there, because we can't do x, we have to do it for something specific. Okay, so put sand timer plus 4 plus 5. Okay, so sand timer is taking the place of x, backwards 4 is taking the place of a, and backwards 5 is taking the place of b. So let's compose sand timer with backwards 4. So sandtimer composed with backwards 4 is equal to backwards 5. So we get backwards 5 plus backwards 5, or composed with backwards 5. I'm sorry, I called the composition law in this group composition law, circle, rather than plus. Okay, I'm sorry about that. It's trivial, basically. We're just using a different symbol, but replace all of these with composition laws rather than plus, because I did call it composition law rather than plus. Okay, so we then get 5 composed with 5, or backwards 5 composed with backwards 5, which gives us sandtimer. Okay, so the answer to this problem here was sandtimer. Now let's ask, what is the answer to the problem sandtimer composed with, let me bring this up. Sandtimer composed with backwards 4 composed with backwards 5. Okay, and let's see that this is different, basically. So 4 composed with backwards 5 is backwards 4. Okay, and I'm going to be really annoyed if just by luck this actually works. Okay, so here is sandtimer composed with backwards 4. I suppose there's a 1 in 3 chance. So what is sandtimer composed with backwards 4? Well, it's backwards 5, so it didn't work, basically. So you can't just move the brackets like that without consideration, basically. It didn't work in our composition law that I just came up with, you know, without any considerations for trying to make it obey any fancy laws. This was not true. However, I'm going to tell you this, it is possible to produce structures where this is true. It is possible, if you come up with a very clever composition law, to make this true, no matter which 3 symbols you put in here, basically. And if it is true that your composition law obeys this, no matter which 3 symbols you pick, then you're said to obey the associative property. Okay, so if the associative property is true, which it is true in the integers, and we all know it's true, that if you add on 5 and then subtract off 5, it's the same as adding 5 to negative 5 and adding that onto the x here. We know it's true within the integers. Okay, then what you can do is you can swap x plus 5 then plus negative 5 for x plus and then 5 plus negative 5. Now 5 is the inverse of negative 5, okay? So what that means is that when you add the two of them together, it makes what is known as the additive identity. It makes the identity of this structure, okay? Now what is the identity? Well, the identity is something that you can compose with any other symbol, and it will always leave that symbol unchanged. So anything plus 0 in the integers is still that thing. So x plus 0 now is just x. So we get, therefore, that x is just 7 composed with negative 5. And that's why we can solve equations in this system, because of all of these things we've just been through. So, what did we require here? We required that any old symbol, because we just picked 5 randomly, we require that any symbol in the set has an inverse, basically, a symbol that you can compose it with to get to the identity. And we also require that there is an identity in the first place. So we require an identity element within the set, which is an element which will compose with any other element in the set to give that same element back again. Okay, so 0 is the identity in the integers. It's the element that you can compose with every other element to give that other element back again. So 0 plus anything will just make that thing back again, and that's true whether you compose it on the right side or you compose it on the left side. So x plus 0 is x, and 0 plus x is also x. Okay, so you have this element which, no matter what side you compose it on, for any other element, it will just give that element back again. Okay, so identity is one of the things you're going to require in a group. Okay, now we didn't have an identity, I don't believe, anywhere in this. No, we didn't have any symbol which composed with every other symbol to give that other symbol back again. Okay, then you also require the associative property to hold for no matter what three elements of the set you pick to put in the X position, the A position, and the B position. So you want associativity. Okay, and then finally you also want the inverses here. Okay, so you want every symbol to have another symbol that it can compose with to give the identity, basically. You want inverses. Okay, so the best way to deal with this then now is to actually see an example now of a group which does obey these, well, a composition law which does obey these, and if you obey these, then you will be called a group. Okay, but we'll see that in the next video.